All right, today we are talking about rational functions, and for some reason, when I tried to cut and paste this guy, it did not show up correctly. But definition for rational functions is that they are quotients of polynomial functions. So what this is supposed to say, there's supposed to be a division symbol there, is that the format is f of x equals p of x divided by q of x, where p and q are polynomials. So when I have one polynomial divided by another, that creates a rational function. Any value of x that causes the denominator to equal 0 must be excluded from the domain. So we've worked on this. When we worked on domain, we've seen rational functions and saying x can't equal this value or x can't equal that value. Now we're going to look at what happens at those excluded values. So in a rational function, an excluded domain value could be a vertical asymptote if it's a value of x that comes from a factor that doesn't cancel. And you're going to see what I mean when we get into the examples by doesn't cancel. The other thing that could happen is that it could be a hole in the graph. So just you're going along the graph and all of a sudden there's one individual point where the graph is not defined. That happens if it's a value of x that makes the denominator 0, but it cancels out when you simplify. So this is why when we did the examples where it asked you to find the domain based on the equation, this is why I said that when you're looking at the domain, you don't just look at the final answer, that you have to look at all the steps along the way. It's because of this. You could have things that canceled, factors that canceled in simplification that still make the function undefined. So when we're looking at asymptotes, it's important that we know what happens with the asymptotes. So with a vertical asymptote, you can have one of two situations. So let's just say that we've got, and let me use a different color here to draw in some pretend axes here. But if I have these axes and I have a vertical asymptote, let's say right here, if the format of my rational function is y equals, or f of x equals, a over some factor x minus h to an odd exponent plus some k value, possibly. That means that the asymptote is approached from opposite directions. So perhaps something like this is what you're going to see with the asymptote. Remember that by definition, an asymptote is a line that the graph approaches but does not touch or cross. So here we're approaching from opposite sides. So one from the negative side, one from the positive side. If you have y equals a over some factor x minus h to an even exponent, and then you've got your k at the end, then when we look at that on the graph, again, putting in our axes and a vertical asymptote, dashed line for asymptotes, it would be approached from the same side, so maybe something like this. So here, both little pieces of the graph that are coming toward the asymptote are on the positive end. Here, one was below and one was above. So that's one thing that's important to know, that the exponent of the factor in the denominator is going to determine where your branches approach from. So in addition to vertical asymptotes and holes in the graph, rational functions can also have horizontal asymptotes. So here are the rules that are straight from Algebra 2 on horizontal asymptotes. If the degree of the numerator is less than the degree of the denominator, then it's y equals 0 for the horizontal asymptote every time. So if numerator degree smaller than denominator degree, y equals 0 is your horizontal asymptote. If the degrees of your numerator and denominator are the same, so p of x and q of x are the same degree, then it's y equals a over b, where a is the numerator's leading coefficient and b is the denominator's leading coefficient. So that's 2 of the 3 possible situations. Less than, equal to, so this one by default has to be greater than if the degree of the numerator is greater than the degree of the denominator. Then there are no horizontal asymptotes if the degree of the numerator is greater than the degree of the denominator. If there is no horizontal asymptote, that is when we investigate for oblique or slant asymptotes. So these two things mean the same. I believe that our text uses the word oblique, but slant means the same thing. So if you were taught in, let's say you took pre-calc and I think the text we use in the high school says slant, it means the same thing. First of all, this can only happen if the degree of the numerator is 1 more, which means we're only looking for slant or oblique asymptotes if there is no horizontal asymptote. If there's a horizontal asymptote, then we know that the degree of the numerator can't be bigger than that of the denominator. So we would not even need to investigate this. So if you have a horizontal asymptote, you're not going to need to look for an oblique asymptote. So not only does it have to be greater than, but it specifically has to be 1 more than. So if the degree of the numerator was 2 more than the degree of the denominator, there'd be no horizontal asymptote and no slant asymptote. To find the equation of the oblique asymptote, we actually have to divide p of x by q of x. Remember that these are polynomials. So this right here is polynomial long division. Sometimes we can use synthetic division, but most of the time we can't. Most of the time it has to be long division. And the answer is y equals the answer from the division without the remainder. So if there's a remainder when you do the polynomial long division, you leave the remainder out. We don't need the remainder. So you are going to see a couple of different things in your homework for 5-3. Actually, I shouldn't say most. The graphs that you're going to be asked to do in this section are transformation-based graphs. In section 5-4, we are going to get to, you can see the whole thing, graph of a rational function, and doing more with those. So the graphs in section 5.3 are transformation based, which is what we see in example 1. It says for f of x equals 1 over x plus 3 squared minus 2, graph the rational function using transformations. So our parent graph for this, or the power function, if you will, is y equals 1 over x squared. So most of us have not frequently graphed 1 over x squared, so it's fine if you don't just know what it looks like. We can always, with any equation, of course, you could graph it in your graphing calculator, but even if your graphing calculator's batteries were dead, we could still come up with an XY table and getting several good points to graph by picking values. If I were to pick -2 for my x and plug it in the parent function, -2 squared is 4, so the y value would be 1/4. If I pick -1, -1 squared is 1, 1 divided by 1, also 1. If I were to pick 0, 0 squared is 0, that's undefined, which is because I'm going to have an asymptote there, a vertical one. Then, if I pick 1 and 2 to match these guys, this y is 1, this one is 1/4. So here gives me 4 different points to use as my parent graph with the transformations. So these take the form y equals a over x minus h to some power. So it could be 1, it could be 2. Those are our only options. So I'm just going to put to the n here and then plus k. So h and k control your shifting, just like they always do. A controls whether we reflect and whether we shrink or stretch, compress or stretch. This part, the exponent, just determines which parent graph you have. So y equals 1 over x squared, the parent looks like this, because if I plot those points that we just came up with here, -2 1/4 would be right here, -1 1. When I get to 0, I know there's an asymptote. Also, if I pick a really big number, let's say I pick like -100, -100, if I plug it in here, this is positive. So this is still above 0. So I know what's happening here is this. It's approaching. I've got like a little branch there. On the other side, 1 1, 2 1/4. So just like we talked about up here, here's the general shape for when I have an odd exponent. I had an even exponent this time. I had squared. So look, similar features. So this is, if it's squared, it's going to look like this. If it's just y equals 1 over x, then those are the ones where it looks like this. And again, if you don't know the points on the parent graph, make a table. That's how you can get the transformations anyway. So, graphing my rational function using transformations. If it said show each stage, you would want to make sure to do that. In this case, it doesn't. So if you wanted to just write out the transformations and move these points that way, you could. This is going to have us shift left 3, because that's my h value, and down 2, because that's my k value, which means left 3 is going to be subtracting 3 from the x coordinates. So I had -2 1/4 I had negative 1, 1. I had 1, 1, and 2, 1/4. So left 3 means minus 3 on all the x's. Down 2 means minus 2 on all the x's. So that gives me negative 5, negative 1 3/4. Here, negative 4, negative 1. This guy, negative 2, negative 1. Negative 1, negative 1 3/4. So here are my points that I'm going to plot. So 1, 2, 3, 4, 5, negative 1 3/4 is right about here. Then negative 4, negative 1, right here. Negative 2, negative 1. Negative 1, negative 1 3/4. Remember that my original graph not only had a vertical asymptote here on the y-axis, it also had a horizontal asymptote on my x-axis. When you draw a graph, if there are asymptotes on the original, the asymptotes need to be on your final graph as well. Look at our shifts. Left 3. So that vertical asymptote that was on the y-axis goes 1, 2, 3 to the left. So you should have a dashed vertical line here at x equals negative 3 because there is my vertical asymptote. Down 2, that means that the horizontal asymptote that was on the x-axis gets shifted down 1, 2. And so now I've got those drawn. So when you connect it, it is actually important that you make sure that it doesn't cross or touch the asymptote. So I'm connecting these branches so that they don't cross or touch. Use the final graph to find the domain and the range. So domain, what is x allowed to be? Well, I can use the function if I want to, but x can be anything except for where there's a vertical asymptote. So in this case, we would say that my domain, it's traveling along nicely from negative infinity. Then when it hits negative 3, it stops, takes a little jump, but then continues on toward infinity. So we are jumping over negative 3 there for our graph. For the range, I don't have any y values down here. So the asymptote is the start of my y values. Again, it gets close to the asymptote, but it's not going to touch it. So I go from negative 2, and then my arrows go up, so all the way to infinity for my range. C, use the final graph to list any vertical, horizontal, or oblique asymptotes. So I've already graphed them. Now I'm listing them. So some of you didn't pay very good attention in the quadratic part of the unit where we talked about the axis of symmetry. And what I told you is that when you write the equation for an axis of symmetry, it has to say x equals because it's a vertical line. The same thing is true here. If I want to list vertical asymptotes, I can't just list the number. It needs to be an equation. A vertical asymptote is x equals whatever the number is that the asymptote is at. So in this case, x equals negative 3. For the horizontal asymptote, likewise, it is a line, specifically a horizontal line. It needs to say y equals in front. What does y equal here? Y equals negative 2. If I have a horizontal asymptote, that means I will not have any oblique asymptotes. So we can write no oblique. All right, so these are the types of graphs you're going to see today. Ones where it's either based on y or f of x equals 1 over x or 1 over x squared. So again, you can make your parent points, and then we're just using our transformations in this format to graph them and find the key features. The rest of it is algebra, and you have to show the work. The point of this is not to graph them in your graphing calculator. You must have the algebra for all of these things. So it asks me to find the domain and all asymptotes of each rational function. So the first thing I need to do is figure out values that might make my denominator 0. So in order to do that, I typically want to factor. So I am going to factor the entirety of my rational function. So numerator, x squared plus 6x plus 5. That's x plus 5 times x plus 1. On the bottom, there's a 2 in front. So that means that this would be a guess and check type factoring. So I know that the fronts would have to be 2x and x in order to multiply to get x squared. I need my middle terms to give me 7x, and 5 is prime. I know if I put the 5 back here that it's going to multiply times the 2x, which gives me 10 already. That's too big. So I'm going to put the 1 back here and the 5 here. Now, again, this is guess and check. You have to check the O and the I of the FOIL. So this gives me 5x. This gives me 2x. That is indeed 7x. So I know I factored it correctly. Again, you don't have to show me that. That's why I'm erasing it. But I need you to know that you do have to check it. You can't just guess and put whatever you want. You have to make sure it actually factors into that. So when we factor, common factors that are separated by multiplication can be reduced. So that means something where the whole thing is multiplied. So this whole x plus 1 is multiplied by the x plus 5. So these two can cancel with each other. That would give us x plus 5 over 2x plus 5. Now, here's the difference. You cannot cancel these x's, nor can you cancel these 5s. They are separated from their counterparts by addition. This 2x separated from the 5 by addition. You can't just hack off pieces of a binomial or a trinomial. It has to be separated by multiplication. These are not, so that's as simplified as the function can get. So now that I've done that, that's going to help me find all of my information that I need. So domain is going to be anything except where the denominator equals 0. So I know that for my domain, that 2x plus 5 cannot equal 0. I also know, even though it cancels in the final answer, it's still part of the function. X plus 1 can't equal 0 either. So if I solve each of these, x can't be negative 1. And this, subtract 5, divide by 2, x can't be negative 5 halves. So x can be anything except for these two guys. So from negative infinity to negative 5 halves, then from negative 5 halves to negative 1, then from negative 1 all the way to infinity. So interval notation is going to be our standard. So make sure that you're writing it correctly in interval notation. There's my domain. The next thing it asks for are asymptotes. So vertical asymptotes. Vertical asymptotes, again, up here it tells us a value of x that comes from a factor that didn't cancel. So it's going to be one of these domain restrictions, sometimes both, but it's the ones that didn't cancel. This x plus 1 did cancel. So it's only this guy. So it's the -5/2. So x equals -5/2 is going to have a vertical asymptote. The -1, there's going to be a hole in the graph there at x equals -1. This did not ask me to list holes in the graph yet. Tomorrow we will have to list them, so we'll be ready for that. But here today it just asked for asymptotes. So vertical asymptote at x equals -5/2. Next, I'm going to look for horizontal asymptotes. So horizontal asymptotes. And when I look at degrees, it's easier to look at the standard form polynomial. The numerator is degree 2. The denominator is also degree 2. So that means degree of the numerator and denominator are equal. So my horizontal asymptote, there is going to be one. It's y equals leading coefficient of the numerator divided by leading coefficient of the denominator. So I write y equals, and then I look. The leading coefficient in my numerator is 1. The leading coefficient in my denominator is 2. So y equals 1/2 is my horizontal asymptote. Remember, if there's a horizontal asymptote, there is no oblique asymptote. So it just says find them. So we can write no oblique if you want. You don't really have to because there's nothing to find. But these are the key features that we're wanting to list. All right, next and last, g of x equals 3x cubed over 4x squared minus 8x. So again, I am going to start out by factoring. My numerator is already a monomial, so everything's already separated by multiplication. I can leave it as is. My denominator, however, binomial, there is a GCF, so I can factor it with that, 4x times x minus 2. So I do not have an x minus 2 factor to cancel with. However, this is 4 times x times the x minus 2. This is 3 times x times x times x. So this x is separated from everything by multiplication, and so are all 3 of these. So this x can cancel with one of the ones that was in the numerator. So instead of an x cubed in the numerator, I now have an x squared in the numerator. And that gives me this guy as my simplified function. Now again, when I go to do my domain, it has to be anything that would make my denominator 0. So this 4x can't equal 0. This x minus 2 can't equal 0. If I divide by 4 here, that means x can't be 0. Add 2 to both sides over here. X can't be 2. So x can be anything except 0 and 2. So my domain, I can go from -infinity to 0, from 0 to 2, and from 2 to infinity. So skipping over the 0, skipping over the 2. Vertical asymptotes. Factors that did not cancel. This x that gave us the 0 did cancel. So it's just this guy, the x minus 2. So that means x equals 2 is going to be a vertical asymptote. For the horizontal asymptote, I would look at the degree. The degree of the numerator is greater than the degree of the denominator, which means greater than none. No horizontal asymptote. So anytime there is no horizontal asymptote, I then have to look to see if there's an oblique asymptote. So oblique occurs if the degree of the numerator is one more than the degree of the denominator. So degree of the numerator was 3. The degree of the denominator was 2. 3 is one more than 2. So that means I need to do division to find a oblique or slant asymptote. So polynomial long division, I have to do 3x cubed divided by 4x squared minus 8x. Now, I left all this space because I don't have any of the other terms. I don't have an x squared, I don't have an x, I don't have a constant. So that means all of those are really 0 for deciding what I need. So when we do polynomial long division, it's very similar to number long division. I start with the front of the divisor and I compare it with the front of the dividend. And I ask myself, what would I need to multiply 4x squared by to get 3x cubed? Well, the x squared to x cubed part is easy. That part's x. We always line up over like terms because that also lets us know when we're done with the problem. But what do I multiply 4 by to get 3? That can be a little trickier because you know it's not a whole number. Specifically, you know it's a fraction and it has to be smaller. So think, 4 times what equals 3? Well, if I'm solving for question mark, divide by 4, question mark is 3/4. So that's what goes here. So what do I multiply 4x squared by to get 3x cubed? 3/4x. Once we write something on the top of our division line in long division, the next thing we do is multiply what we just wrote times my divisor, all of it. So I do 3/4x times 4x squared, which gives me 3x cubed, and 3/4x times negative 8x. So 3/4 times negative 8 is negative 6. X times x is x squared. So I get negative 6x squared. The next step in long division, after you multiply what was on top times what was in front, is to then subtract, which this is the only time you'll hear me say subtract. Because typically, I say change the signs and add. Yes, it's the same thing. But here's what happens. When I say subtract, people put the minus here, and they forget that this then becomes a plus. Because if I'm subtracting a negative, it changes that. So that's why I say change the signs and add. And I actually circle them so that I can indicate to myself that, hey, you remembered to change that. Now I can add the columns. So 3x cubed plus negative 3x cubed is 0. Those cancel out. 0x squared plus 6x squared is 6x squared. The next step is typically to bring down the next term. And then I start over. So then I ask myself, what do I multiply 4x squared by to get 6x squared? So what do I need to multiply to get from 4 to 6? Again, if you don't know 4 times what equals 6, then write it out like this. The question mark is 6/4, which reduces to 3/2. So 3 over 2 is what I write up here. It's x squared and x squared, so there should be no variable here, but you should know that anyway because this was a plain x. The next term should be a constant. We always reduce the degree by 1 as we go. So now 3 halves times 4x squared is 6x squared. 3 halves times negative 8x is negative 12x. After I multiply, I change the signs and add. So add my columns, that gives me 12x. If I were to do this again and try to start over, I can't because I'm out of space here. This right here is the remainder, which when we do polynomial long division, you have to know what to do with that remainder. And in Algebra 2, they teach you what to do with that remainder. Here, we don't need the remainder, so we're not going to talk about that because the only part we need is what's up here. That is the equation for my oblique asymptote. So my oblique asymptote, which I am going to list, is y equals, remember it has to be the equation of a line, 3/4 x plus 3 halves. So these then are my final answers. If you have listed an oblique asymptote, you better have division to prove where you got that equation. If we are doing domain, you need to have factoring. Again, everything here is to be algebraic. You are certainly welcome to use your graphing calculator to check your work, but it needs to be done with the algebra. All right. We will answer any questions you have on what I went over here when I see you next.